I was talking before I unmuted the microphone. I was talking about the tension members. We're now going to design tension members. The analysis part is done. So, so we're ready to do the design. The design and the analysis are going to be very closely related in that the only portion of the design that we can really accomplish without doing an analysis is to calculate and find what the minimum area of the member is that we're going to that we're designing. So what will happen is if we take the loads that are given to us, this is the example problem that you see. The service dead load is 70 kips. The service live load is 110 kips. And that's, since it's a tension member, the loads to a tension member have to be in pounds or kips. So if I told you, well, the tension load to this wide flange section is 100 pounds per square foot. That doesn't tell you diddly squat. You can't design a tension member for 100 pounds, 100 pounds per square foot of load unless you know what the area of the structure is that this member will support. So you can take that load, 100 pounds per square foot, and say we're designing a tension member and we're hanging a canopy from this member. If I know what the live load of the member is, and if I know what the tributary area to the tension member is, and the area would be in square feet, then I can calculate the load in pounds or in kips. And that's what we have to have in doing tension members, is I have to know what the dead load and live load, those service loads, I have to know what those are. The problem also asks us to select the lightest section, and in fact it says select the lightest W section. That's because we buy structural steel by the pound. So if I were to go if I were to go over in Fort Worth to North Texas Steel and tell them, hey, I'd like 15 W12 by 26s, 20 feet long. Well, they'd fabricate those for me, load them on my truck, and then they'd hand me a bill, and the bill would say, aha, you bought 3,000 pounds of steel. The steel costs $2.50 a pound. You owe me 7,500 bucks. So I might want to look at my design again, because if I can design a lighter section than a W12 by 26, for instance, say, oh, I can design a 12 by 19 and save 7 pounds per lineal foot. That 7 pounds per lineal foot would factor in to the total weight of the beam, the W sections that I'm buying, and correspondingly reduce the cost. Now, included in the problem, the second sentence is the member is to be 18 feet long. Why do I care how long it is? That's what we talked about last time, is that these members have to have a minimum slenderness ratio, maximum slenderness ratio, not to exceed 300. So what that does, what that 18 feet long does, we're going to have to go back and check the slenderness ratio of the member to make sure it doesn't exceed 300. That means that we have this load in this W section, and if it's 100 feet long hanging from someplace, then it probably exceeds the slenderness ratio and would not be appropriate to use. Then included in that sentence, it says it is assumed to have one line of holes for 1-inch diameter bolts in each flange. Assume that there are at least 3 holes in each line, 4 inches on center. So that should tell us something there. From our analysis, now we know that we have a U factor. We need to figure out what is the effective net area of whatever the member is that we choose. We need to check the effective net area with 3 holes, 4 inches on center, and 4 1-inch diameter bolts in each flange. So we'll need to do that check. The last thing is the steel is A572 grade 50 steel. I think all of our steel will be that grade, but be sure you can't do the problem if you don't know what the grade of steel is. So that has to be given. So how are we going to proceed to do this? Where do we start? Well, the first thing we have to do is we need to find the factored load, the factored tension load to the member. So we've got to use the load combinations that we learned in chapter 2. This member only has dead load and live load. So if we went back to chapter 2, looked at the load combinations, we would find that the second equation down that says the ultimate load, or the factored load, is equal to 1.2 times the dead load plus 1.6 times the live load. And then I think that equation says plus something, 0.5 times the roof load. We ain't got any of that. So we'll factor the load by saying we'll take the 70 kip dead load, multiply it times 1.2. We'll take the 110 kip live load, multiply it times 1.6. And here's our load, 260 kips. That is the factored load. So we need to know what area member, and that's the only thing we got to go by, is what area member will carry 260 kips. So we'll go back again to the beginning of chapter 3. If we base the area of the member that we're going to design on its gross area, then we'll take the factored load, 260 kips, divided by phi times F sub y. This is the stress equation, and we get 5.78 square inches. So if we were designing this member based on the gross section, and we weren't going to consider the holes or any of that sort of stuff, then we would look in the steel manual for the lightest W section that has 5.78 square inches of area. Well, that
Professor?
doesn't, yeah.
For F sub y, we need to look at that in the steel manual, right? So would we get that from the A572 grade 50 steel
That's correct.
information?
Yeah, the
Okay.
F sub U, remember, Virginia, the F sub U, see right down here in step number 2, now we're going to use F sub U. So I would go back to table, wait, I got it, just a sec. Just a minute. Okay, here's part one of the steel manual. Now the question that you're asking is, where do we find the values for the A572 grade 50? First of all of the W shapes that we design will be grade 50. That's all that's in the manual. However, if we go to, let me get back here to the beginning, and we'll go to that table in the manual where we can get the F sub y and the F sub u. That's an important point. So we need to make sure that we find the proper grade of steel. Rather than, rather than flipping through all those pages, if you recall, table 2-3 is just a second. I'm going to pull it up on the screen here.
Sorry, Professor, I didn't mean to
No,
make the
it's okay.
class come to a stop.
No, we're not stopping. I'm working on my end. Okay, I got it. Wait, here it comes. Wait for it. Okay, here's table 2-4. So the steel that we're going to be using typically as we look at the wide plane sections on this on table 2-4, the A572 is high strength steel. So there's A572, and it says we're using A572 grade 50. So A572 grade 50, there's F sub y is 50 KSI, and F sub u is 65 KSI. Now, there's not much change between the A572 and the A992. So you'll see in a lot of these problems where I'll say that the steel is A992 instead of A572. And the reason that I do is because of this black box. Remember, that's the most commonly rolled shapes are W shapes, and they're most commonly rolled as A992 steel instead of A572 steel, but the strengths are exactly the same. So there's no difference between them. So there's where that comes from.
Thank you.
Absolutely. So the F sub y is 50 KSI, and the grade 50 gives that away. Now the 5.78 square inches leaves us with searching in the manual. Let me get the steel manual up. Okay, here's the steel manual, and we'll zoom in a little bit. Not quite that much. All right, so the areas of the members are given. Remember, the area is here in the first column. We're looking for a member that has an area of 5.72 square inches. So one of the difficulties that we run into is sometimes this is kind of tough. This is more difficult than Goldilocks trying to figure out which of the three bears' beds is most comfortable to her, because here we can see that these areas of these W27s is way bigger than what we need. So we'll get to some smaller size members. The 21s. Now we're looking for a member that's only 5 square inches. So here we can go, this member down at the bottom. The member down at the bottom is a W16 by 26, and it has an area of 7.68 square inches. So we're getting closer, all right? And we want the lightest section that would weigh, that would be 5.72 square inches. So if we move to the W14s, you can see all of them are going to be heavier. We'll move to the W12s, and now we're talking, okay? Now we look down at the bottom of this table, and aha, there's a W12 by 22, 6.48 square inches, 12 by 19, 5.57, so we know that won't work. The 12 by 26 is 7.65, so that'll work, but we're looking for numbers as close as possible to 5.72, but greater than, not less than. But the confusing part of doing this is, there's the 14 by 22. It's got an area of 6.49. So in doing the design, it appears that the area of a 14 by 22 and the area of a 12 by 22 is about the same. So in the design, if we pick a 14 by 22, or should we pick a 12 by 22, we're picking the lightest section, so it doesn't matter. Either one would cost the same. Either one would be the lightest section. Now we can go to the smaller sections. Here are the W10s, and we could go down the W10s. And for instance, there is the W10 by 22, 6.49 square inches. Do you see a pattern here? The W10 by 22, the W12 by 22, and the W14 by 22 all have just about the same area, 6.49 square inches. So is it possible there are multiple solutions to our design problem? Absolutely yes. So this is not a multiple choice course. I'm not going to say, hey, which section is right? The W10 by 22, the 12 by 22, or a 14 by 22? How can you answer that question? Well, it's all of the above, right? So we need to narrow down our selection. Now we need to narrow down the selection, but we still have a couple steps to go. Our sections that we're looking at are based on the gross area of the member. So we know that the net area of the member is going to be less than the gross area. So we need to worry about the holes, those darn holes that are in this member. Okay, so right, let me get this up. Okay, so 5.78 square inches is the magic number. Now we're going to assume a U value of 0.85. Go back to table D 3.1 and you'll find that the U value for wide flanges, if they are attached together, if they're attached with three bolts in a row, that the U factor is 0.85. The thickness of the flange is just a wild ass guess. Okay, the members that we were just looking at, the flange thicknesses were about 3/8 of an inch. So we've got to make an assumption someplace. So we're going to assume a flange thickness of 0.425 inches. And you get that from the steel book, because once again, the steel book will get the steel book back up. So the W, for instance, the W10 by 22 that we were looking at has a flange thickness of 0.360 inches. Okay. So so the 0.425 is just a guess on our part. Notice if you go up a little bit higher, the W10 by 33 has a flange thickness of 0.435. Why do we care? Well, we care because we have to make an estimation of what the minimum net area is going to be for our member. So if we say the thickness of the flange, I don't care, say it was 1/4 of an inch thick or 1/2 an inch thick or somewhere in between, let's estimate what the minimum net area is. Well, the minimum net area, remember, is based on, this is the second equation, the tensile capacity based on the minimum net area right here. So we got PU divided by P sub T times F sub U times U. The U factor will give us the net area. So right here, we'll put the load in, 260. The 0.75 is the P factor for that equation. The 65 is what we just looked up in the steel manual. The 0.85 is a rough value for U. That's probably pretty close. And then Right here is now we're compensating for the holes. Okay, we compensate for the holes. We need to add them back into the area. So when we subtract out the holes, we need to stay above our minimum area. So we're going to say, hey, these holes, 1-inch diameter bolts, that's 1.125" holes. The 4.25 was our guess at the thickness of the flange. And we got 2 holes, right? There would be 2 holes in that wide flange because it says 1 line of holes for 1-inch diameter bolts in each flange. When you count the flanges on a wide flange, it's got 2, a top flange and a bottom flange. So that means that there's 1 line of these holes in the top flange and 1 in the bottom flange. So we're going to take and subtract out 2 holes. And the reason, remember, the reason we're doing that is we're taking and trying to find the net area of this wide flange section. And wait, I'm writing over here, but y'all can't see what I'm writing. So it would be a good idea if I just a second. Okay, here's the wide flange. It's got a row of bolts in the top up here. These are 1-inch diameter bolts, and say it's got another row of 1-inch diameter bolts down here. If you look at this in plan, it looks like this. We've decided that this web thickness, the flange thickness, is 0.425 inches, and the holes look like this. So I got these holes in the top flange matching holes in the bottom flange. So this line would be the gross area. This line would be the net area, and it goes through the top and bottom flange. So I got 1 hole here and then 1 hole down in the bottom flange. So that's what we have. That's what we have to work with. So we're going to subtract 2 holes. When we're going to add back in the 2 holes that we're going to have to subtract. So now our area is increased to 7.23 square inches to make the allowance for the presence of the holes. Let's do step 3. We'll check the minimum radius of gyration. The minimum radius of gyration needs to be L over 300, 18 feet. The radius of gyration is given in inches, so we need to convert the 18 feet to inches. So it is 12 inches per foot divided by 300. Our member better have a radius of gyration greater than 0.72. Okay, so now we're boldly ready to pick a member. Well, the only issue we got with now boldly picking the member is we went through and looked at members that had an area greater than 5.78. So when we added in the area we'd need to compensate for the holes, now our area is up to 7.23. We're going to try a 6 by 25, and the reason that we're going to do that is because this is a trial and error process. We can no longer pick from a book or pick from a catalog. We could wait for the software to give us a member size, but we're going to do this by hand. We're going to find a member now that has a gross area greater than 7.23 inches. So if we go to the steel manual and pick that out, let's see, what do we got? What do we got? The here, okay, here's W6 by 25 in the manual, and sure enough, it's got an area of 7.34 square inches. Notice in the manual that all of the shapes are listed in inverse order by depth and by weight. So if we go back one page, we'll go back to the W8s, okay? And down here at the bottom, there's the W8s. Is there a W8 that weighs less than the W6 by 25 and has the area that we need? Well, we'll read up the W8s and we get right there. A W8 by 28 has 8.25 square inches of area. It appears to be a winner, except it's heavier than the 6 by 25. The 6 by 25 weighs 25 pounds per foot. The W8 by 28 weighs 28 pounds per foot. Well, let's check and see. Maybe a W10 works. There's a W10 by 26, 7.61 square inches. It comes within a gnat's ass of working, right? It's got the area that we need, but it's still heavier than the 6 by 25. So it turns out we in fact have picked a good member, the W6 by 25. That appears to be the lightest section that will give us an area of 7.23. The thickness of the flange was given at 0.455. That's in, once again, if we go to our 6 by 25, all right, you need to know how to read the manual. We'll come across to the flange thickness, and there it is, 0.455. So that's the thickness of the flange. So the wild guess at 0.425 really wasn't too bad. So there's the thickness of the flange, the radius of gyration. Okay, the radius of gyration of the 6 by 25. Remember when you get your manual that these members, the properties are on 2 pages at a time. So the right-hand page continues with the properties of the 6 by 25, and we're going to read across. There's the radius of gyration about the x-axis of 2.70. There's the radius of gyration about the y-axis of 1.52. The problem doesn't define how this W6 by 25 is oriented. So I don't know whether I should take the properties about the x-axis or the y-axis. So what am I going to do? Well, I'm going to pick the smallest value of R and use that in my design. That's the most conservative. So I know that the radius of gyration can never be less than 1.52. So that's what I got, 1.52. Now this becomes an analysis problem, all right? We need to check what's the capacity, what's the nominal strength of a 6 by 25, first of all, based on the gross area. The nominal strength is 0.9 times 50 KSI times 7.34 square inches. That's 330.3. So based on the gross area, we're good to go. Now, based on the net area, we need a net area that is greater than the area of the 6 by 25. So the net area becomes 7.34 square inches minus the area of the two holes. That's 6.32 square inches, and that's no good because right here it says in step 2 we have decided we need a minimum net area of 7.23 to make this member work, and 6.32 don't get us there. So now we're screwed. Now we need to go back to the steel manual. And remember when we looked up the 8x28, the 8x28 was good because it was the smallest W8 that had an area greater than 7.23. So let's try that. And again, this is the Goldilocks approach. We're doing trial and error. Net area, the gross area of the 8x28 is 8.24. If you were to look in the manual, the thickness of the flange and the radius of gyration are given. So now we can check it, okay? And here's the check. First of all, based on the nominal strength of the member on the gross area, duh, that's kind of a stupid calculation. We know it's going to work for that. The net area now is 8.24 minus 2 of the holes times the thickness of the flange. We get 7.20 square inches, which is pretty close to the 7.23 that we need. So let's call it good, all right? We're building a building, not a watch. So we'll say we're close enough. We need to find the U factor. In order to find the U factor, we need to know what the X bar or the Y bar is for the U. That's given again in the manual for a W8x28 at 7.34 inches. There's the calculation for U. U actually comes out to be 0.91. We can't use a value less than 0.9 or more than 0.9. So we use 0.9 as the U factor. We guessed 0.85, so we're in good shape. If we'd have guessed 0.85 and the actual U was 0.6, then we'd have a problem. We'd need to recalculate. So we're safe so far. We'll check the L over R ratio. The radius of gyration of the 8x28 is 1.62 inches. That gives us a slenderness ratio of 133. That's less than 300. Yay, that works. Now we'll check the nominal strength of the member based on the tensile fracture capacity. Based on equation number 2, 0.9 times 65 KSI times 0.9 times 8.24 gives us 433.8 kips. So the 8x28 is the winner. So the design involves finding the area that we need. Once we find the area that we need, then we can find the U factor based on the connection properties of the member, and then from that we'll check the nominal strength based on the gross area and based on the net area. Here's another example. This one, yeah.
That question, just so I understand, in the very beginning, why did we only calculate for 2 holes? It says there was a line in each flange, and I know before when it said that we did it 4 holes because there's 4 flanges in W section. So how do we decipher if there's only 2 holes or if there's 4 holes?
Okay. Here's a picture of the beam. Here's the section of the beam, okay?
Right.
So if this is the section of the beam, when I'm looking down from the top, the tensile force is this way, all right? I'm putting this member in tension. So when I figure the net area, I'm going to figure the net area on a plane that is perpendicular to the holes. So looking at this again, if I had a plate, okay, we did example problems with a plate. So here's one plate, here's the other plate, okay, and I got 6 holes there, and I'm going to apply a tension force to this plate. So I can find this plate based on the gross area, ignoring the holes. What's the gross area of the plate where there aren't any holes? Then the net area is based on taking out one hole.
Yeah, so I understand that, but like
So
in the
in-
section in the top left, so you have the section of the flange and
Right.
or the W flange, and when it says that there's one line of bolts in each flange,
Right.
we had a problem like that before, but instead we have 4 because like looking at that top left one, there is a bolt in that flange and the other flange.
That's in fact, yes, that's correct. Here's the isometric. There are 1, 2, 3, 4. I don't care. There could be a dozen holes in a row. All right, and then they're the same. There's holes in a line in the bottom flange also. So if I got holes in the bottom flange and the top flange, then the failure plane goes through one hole in the top and one hole in the bottom.
Okay, but so I guess the question is, how do we know? Because there's been a problem before where like that was also mirrored on the other side, is what I'm saying. So like,
okay, yeah, okay. If we had 2 rows of bolts like this, then we take out 2 holes in the top and 2 in the bottom, or 4 total.
so when it says there's one line in each flange, do we consider the top of flange and the bottom of flange, or is each side?
No, that'd be correct. Again, here's the beam. Okay, if it's got 1 row of holes in the top flange, that row of holes looks like that. Okay, and it doesn't make any difference how many there are. Then in the bottom flange, there's a row of bolt holes also, and it really wouldn't make any difference even if there would typically be a matching number of holes in the top and in the bottom, so that we could attach another member to this wide flange. But again, the number of holes in the line don't make any difference. The actual, what makes the difference is the line itself. So when the problem says 1 row in each flange, that means that you have 1 row in the top flange, 1 row in the bottom flange, which means you'll subtract out 2 holes in doing the net calculation. Now, if the flanges, obviously, if we had the condition where we've got 2 rows of bolts, okay, and again, if for instance, let's take these 2 plates and we'll say, no wait, those 2 plates, here's the wide flange. We're looking down now. This member's a wide flange. So there's the web, and I got 2 rows of bolts in the flange. If I have 2 rows of bolts in the top flange and a matching 2 rows of bolts in the bottom flange, then when I do the net area calculation, I have to subtract out 2 holes in the top flange and 2 in the bottom. And I could add a row of holes in the web. So if I added them in the web, I'd go through one line of holes in the web. I'd have to subtract out one more hole, because in here, if I put a row of holes in the web like that, then I would go through the hole in the flange, the hole in the web, and then the hole in the bottom flange. So I'd subtract out 3 holes.
Okay, I think I got in the roundabout way. I guess my question was really because we've done a problem where it was 2 holes, but I guess it wasn't one in a row. It was 2 rows on a plate that just so happened to straddle, I guess, the web. If that makes sense. So I was just trying to make sure I know like what to look for when it says 1 row, and I don't mistake that for meaning 1 row basically on each leg of the flange. And so it's 1 row, which means only 2 holes, not 4. That's like the clarification.
And your point is well taken, because having 1 row of bolt holes, 1 row of bolts in the top flange and the bottom flange in itself sounds kind of stupid. I wouldn't really try to connect 2 members together with only 1 row of holes in the flange, because just like you said, the row of holes would have to be on one side of the web or the other. So you get an eccentric connection, because the holes are not centered in the middle of the wide flange because the web is in the way. So very, very seldom. And the example problem is for illustration purposes only. In reality, I would probably bolt that. I'd probably bolt this wide flange with 4 bolts like that, right? And then 4 bolts in the bottom flange. And that way, if I had 4 bolts, the failure plane would go through 2 bolts in the top flange, 2 in the bottom flange, and I'd have to subtract out 4. That would be the typical connection.
Okay, yeah, thank you. I appreciate that. Yeah.
Absolutely. Okay, we will finish. We'll design a few more members on Monday, and I'll have your exam for chapters 1, 2, 3, and 4 ready on Monday, and we'll walk through it, and you'll have something to keep you busy next week. We wouldn't want you sitting idly. Okie dokie. Thank you all. I appreciate it, and have a good weekend. We'll see you on Monday.
Thank you, Professor.
Thank you.
Thank you, Professor. See you Monday.